Welcome. We are going to continue on our journey. We are going to start discussing chapter 3. In this chapter, we're going to be discussing more about equations, compounds, molecules. We are going to start naming compounds. Long chapter. Let's start by seeing how, realizing how everything is made out of just simple elements. Very, very simple elements. Everything, your fruits, your vegetable, everything, when those elements combine, they form these amazing substances, these tasty fruits, vegetables, or it also create, when they combine, they can also form some toxic substances. So it just depends. And the ratio what they combine is very important. For example, we have sodium, Na, right? And capital N, lowercase a, and we have chlorine, capital C, lowercase l. These are two elements. They're two atomic elements. No, this is atomic element, and then chlorine, it's Cl2, so it's molecular, right? Chlorine by itself is very dangerous because, sodium by itself is very dangerous because it likes to get rid of one electron, meaning it becomes a cation. Very reactive when you expose it to air. Chlorine, on the other hand, is this toxic gas, this yellow gas, and is very poisonous. So individually, both of them are dangerous. However, when you combine them, when you combine the ratio 1:1, one sodium and one chlorine, you create or you synthesize sodium chloride, which is not as dangerous depending on how much you ingest daily. You know, some of us probably do it too much, but it's something that is not everyday life, so it's not as common, right? So sodium chloride is table salt. The properties in general are not going to be as dangerous as just as sodium and chlorine. Going back to just elements itself, it's going to be really rare to just find an element, just find sodium just laying around. Usually those elements like to form compounds. They do not like to be by themselves. This is because energy. They're more stable when they are in a compound, and the way they come together is through a bond. And we're gonna see how we have different type of bonds. So they are going to come in a fixed ratio, right? This goes after defined proportion, the law of defined proportions. So depending on the ratio that they combine in, they're gonna form different compounds. Going back to mixture, which you already went over, but a mixture is when you have different amounts of different elements in there. For example, here we have a molecule. The reason why molecule, because O2, right? And we have hydrogen, H2. It's a molecule. This is considered a mixture of different molecules. A chemical compound, it's going to be when you do still have different elements, but they are attached together through a bond. So for example, water, H2O. This is a compound because now it's a mixture of different elements. Compounds are composed of atoms held together by a chemical bond. We are going to have two types of bonds: ionic bonds and covalent bonds. It is very important to be able to understand these two bonds. In an ionic bond, is going to be formed between metals and non-metals. Covalent bonds are going to form between non-metals. And we're gonna get into them. We're gonna dive a little bit more so we can understand it. This, if you understand these two bonds, it's going to make your life very, very easy. Remember, if you recall that the metals are going to be on the left side of the periodic table. That is your group 1 through roughly group 13. Those are your metals. And then everything else becomes non-metal. In an ionic bond, is going to occur when you have an element that is a metal, such as lithium, and a non-metal, such as chlorine. So when you have a metal and a non-metal, what's going to happen is that metal is going to transfer the electron to the non-metal. So in an ionic bond, there is a transferring of electrons. The electron is always going to flow from the metal to the non-metal. The metal, because it's giving away the electron, it's going to become a cation. It's going to become lithium plus. The non-metal, because it's receiving the electron, it's going to become an anion, Cl minus. So just to go over a little bit again, ionic bond, it's going to exist between a metal and a non-metal. The metal will transfer electrons to the non-metal. The metal will become a cation carrying a positive charge. The non-metal will become an anion carrying a negative charge. The reason why these two, the metal and the non-metal, become together is because they have a strong attraction. Opposite charges attract. Positive and negative are going to attract, and it creates this force, which is a very strong force. We see an image here where we see the sodium, which is your metal, that has 11 electrons, and we have the chlorine. In this case, the sodium is going to donate, so went from 11 to 10 because the sodium is giving the electron to chlorine, making chlorine 18 electrons. So therefore, the chlorine becomes the anion and the sodium becomes the cation, forming sodium chloride. Okay, so make sure you understand ionic bonding. On the other hand, we have covalent bonding. Covalent bonding is going to exist between two non-metals. For example, if I put carbon and oxygen, both of them are non-metal. They're going to be on the right side of your periodic table. When they get together, the charges are going to be similar. So there is not that opposite attraction. What is going to happen is they are going to share the electrons. In a covalent bond, the electrons are being shared. And when they are, so there we say they are covalently bonded and they become molecular compounds. Molecular compounds come together through a covalent bond. A covalent bond takes place when you have two non-metals. When we represent a chemical formula, which means you have a ratio of different elements, we have different way of representing these chemical formulas. For example, this is a chemical formula. Notice H2O, that is a chemical formula indicating that you have 2 hydrogens to 1 oxygen. Carbon dioxide is a chemical formula. Sodium chloride is a chemical formula. Carbon tetrachloride, it's a chemical formula. Now, as I mentioned, we have different ways of representing it. The same idea, we're still coming across the same. Like, for example, okay, I can characterize you as being a female or a human or a teen or the race you are. So there's different ways of characterizing you. Same thing when it comes to a chemical formula. We have what's called an empirical formula, which gives you the least amount of information. We have the molecular formula, and we have the structural formula, which gives you the most information. So let's go over the difference of all those three types of formulas. The empirical formula is going to give you a relative number of atoms of each element in a compound. Just pretty much kind of gives you an idea what you have in there. In a molecular formula, it's better because it actually tells you, that actually tells you exactly how many atoms you have of each element. For example, this is considered the molecular formula. But remember that one of the laws was to represent it in the lowest ratio. So in order, basically, we always represent the empirical formula. How do we go from the molecular formula to the empirical formula? When the molecular formula is given, you're going to locate the greatest common factor. In this case, the greatest common factor of 8 and 4 is 4. So what we're going to do is divide both numbers by 4. So carbon 4 divided by 4 is going to be just 1. And 8 divided by 4 is 2. So therefore, the one I'm circling becomes the empirical formula. So to go from the molecular formula to the empirical formula, you just want to locate the greatest common factor. For here, we have B2H6. B stands for boron, H stands for hydrogen. The greatest common factor is 2. Therefore, the empirical formula becomes BH3. There will be times where there is no common factor, or the common factor is just 1. I shouldn't say there isn't, it's just 1. Therefore, the empirical formula and the molecular formula become the same. Here, carbon tetrachloride, the greatest common factor is 1. So when you divide it by 1, it comes out to the same. The structural formula is the one that will give you the most information. The reason for that is the structural formula is gonna let you know how those elements or how those atoms are connected. For example, here we have H2O2. So how do you know that it's not connected HHOO? Could be connected like that, right? Later on, you're gonna realize how this is not possible. But for now, let's say you don't know. So the benefit of having the structural formula is that it uses lines, these lines, to represent covalent bonds. Those lines represent covalent bonds. And why is it that they're covalent and not ionic? Because hydrogen is a nonmetal and oxygen is a nonmetal. So therefore, there is this line. It's a covalent bond, not an ionic bond. So as you can see here, we see how they are connected. So the structural formula is gonna give you the most. The formula that you use is gonna depend on how much information you're willing to communicate. So it's going to depend on the problem, right? Depending, for example, in my case, I'm teaching you. So I'm gonna, depending on what kind of information I wanna get out of you, I'm gonna give you a certain formula. I might give you a molecular formula and give you an empirical formula and ask you for an empirical formula. In the real world, you have all these choices, but it depends on what they're asking, right? So depending on the situation, so which structure, which formula you use is gonna depend on how much you're willing to communicate. Just keep in mind that the structure formula is gonna communicate the most information, and the empirical formula is going to communicate the least information. In the lab, you are going to be using balls and stick to kind of just be able to formulate a 3D versions of these compounds. If you were to have these amazing eyes and be able to see the compounds itself, that's how they will look. However, in lab, we don't really use that because we want to be able to see the angles in between. In this space filling model, we don't see the angle between oxygen and hydrogen. We don't see that angle. But when you use balls and sticks, it makes it easier for us to kind of identify that angle. In the lab, just this is like our own general language, we have certain colors to represent different atoms. You don't have to memorize this, but sometimes when you're reading an article or when you're reading a textbook, you're going to see that chlorine is represented by green, carbon is going to be representing black, hydrogen is going to be representing white. You don't have to worry about it. They will always let you know, but this is just common that it makes it easier so you don't have to refer to the table to kind of tell you what color what does the color mean. Here we have a summary of all different models that we have, molecular models that we have to represent a different compound. We are going to be using the molecular and the structural formula very heavily. And in lab, you're going to be playing around with the ball and stick. And if you decide to do computer science, you're going to be able to use the space filling model. Here's a table where notice that you see the empirical formula, the molecular formula, the structural formula, the ball and stick model, and the space filling model. Okay, so this completes the first part. I know it's short, but this is the end of that topic. We are going to move on later on and pretty much identify this large table that you see in front of you. Let's continue with our discussion. Now what we're going to start doing is going over these definitions, which we already know about it. We're just gonna give examples to make sure you guys understand, especially when you're doing math. You're gonna be able to, you need to able to understand what is a molecule versus what is a compound, and versus if it is a ionic compound, if it's a molecular compound. So let's start with our elements, atomic elements. Atomic elements are going to be those elements that can exist as a single atom. For example, gold or silver or platinum. You see where my mind is, right? Those exist by themselves. Those are considered atomic elements. Oh, here's another example. Sodium, neon, potassium, magnesium. They can exist by themselves. Those are considered atomic elements. We also have molecular elements. Molecular elements are going to be those that need to exist with another element. They do not exist by themselves as single atoms. Instead, they're gonna exist as either diatomic or polyatomic molecules. Diatomic will be the seven that I went over, have no fear for ice cold beer. Polyatomic would be something like phosphorus because it's like P8. It likes to exist with multiples, right? Here we see an atomic element such as mercury. Here we see a molecular element such as chlorine. Just to give you a recall, these are the 7 diatomic elements. We also have polyatomics. The polyatomics are going to be your phosphorus, sulfur, and selenium. Everything else, the ones in yellow, represents your your diatomic elements. Notice that they're all non-metals. Okay, so be able to differentiate from an atomic versus a molecular element. Then when we have compounds, meaning that we're gonna go on this side of the chart. When we have compounds, meaning that we have atoms that come together, either two nonmetals or a metal or a nonmetal. So molecular compounds are going to be when you have two or more nonmetals come together. They are going to be different. So they have to be nonmetals, and they are going to come together through a covalent bond. And remember that when you have a covalent bond, you are sharing electrons. So those are going to consider your molecular compounds. Your ionic compounds are going to be when you have a metal and a non-metal joined together through the opposite attraction, because you have a cation and an anion, a positive charge and a negative charge. So those are going to be your ionic compounds joined through an ionic bond. For ionic compounds, always are going to contain a positive and a negative charge. The sum of charges are going to create that attraction, and they have to equal to each other. So if you have a +1, you're gonna have a -1. If you have a +2, you're gonna have a -2. The charges of the represented elements can be predicted from the groups, and this is a very important fact. We can predict, and this is on the main group. Remember how we had the main group in the transition metals? We can actually predict the charge that that specific element would like to form. Transition metals are not as predictable because they can carry multiple charge. So hence, we're not gonna be able to predict those charges. But for the main group, we are going to predict those charges. How do we write chemical equations? Chemical formulas, not chemical equations. Well, if I tell you that aluminum likes to form a 3+ charge, meaning it likes to give 3 electrons, and oxygen likes to receive 2 electrons, what's going to happen is that the superscript, just the number of aluminum, is going to become the subscript of oxygen, and the superscript of oxygen is going to become the subscript of aluminum, creating aluminum 2 and oxygen 3. Same thing with magnesium. So the superscript becomes the subscript, the superscript of oxygen becomes the subscript of magnesium. So they kind of crisscross. Now, remember how I told you that you can predict the charges? Well, here you go. These ones I highly recommend you memorize. Notice that these are the charges that are not gonna change, along with aluminum. Zinc is never gonna change. Gallium is never gonna change. Silver is never gonna change. They're always going to carry that charge. So everything on group 1 is gonna carry a +1. Everything on group 2 is going to carry a +2. Halogens are going to carry a -1. The oxygen family is going to carry the -2, and then we have those odds that are going to be there. Notice here we have a molecular compound and an ionic compounds. Ionic compounds are usually going to be crystalline. When we are dealing with molecular compounds, we usually have this, we say the molecule of water. However, if it's ionic compound, we said the formula unit, just another terminology. No, don't worry so much about it. Here's a table of different characteristics versus ionic and molecular. Just kind of a general idea. For example, ionic compounds are always going to be solid at room temperature. A molecular compound can be found on all 3 states. The solubility of water. So ionic compounds are soluble in water. Molecular compounds may or may not be soluble in water. Ionic compounds are good conductors of electricity. molecular compounds are not good conductors. We have another term that I want you to start becoming familiar with it, and that's going to be the word polyatomic ions. The word ions means that they carry a charge. Polyatomic, poly means many. So this is going to be a group of atoms. They like to exist together and they like to carry a charge. So for example, nitrate. This is a polyatomic ion. It likes to exist in those ratios and it likes to carry a negative charge. Here we have a carbonate. It likes to carry that ratio and it likes to carry a -2 charge. Then we have chlorate. And yes, those names sounds like complicated, but you actually are gonna have to memorize some of them. So those are species that it's a little family that likes to exist together and likes to carry a specific charge. So the proper definition, it's going to be, it's a group of atoms that have a charge associated with them. We are to determine the total of a number of each type of atom in a compound containing a group within the parentheses. We're gonna multiply the subscript outside the parentheses by the subscript of each of the atoms inside the parentheses. If you don't know what that means, let me explain it to you. For example, here we have magnesium nitrate. If I ask you how many magnesiums, you will tell me there's 1 magnesium. How many nitrogens? Well, the two outside the parentheses applies to the nitrogen and to the oxygen. So in this case, you have 2 nitrogens. How many oxygen? Well, here inside the parentheses, there's 3. That 3 applies only to the oxygen. 3 times 2, you're gonna have 6 oxygens. So that's how many atoms you have. So in total, here you have 9 atoms. Just to give you a summary of the ionic compound formulas, ionic compounds always contain positive and negative ions. In a chemical formula, the sum of the charge of positive ions, which are going to be your cations, must equal the negative ions. So whatever, if you have a +3 cation, you must have a -3 anion. The formula of ionic compounds reflect the smallest whole number ratio of ions. We always want to represent it in the smallest ratio as possible. The charges of the represented elements can be predicted from the group. So that's the periodic table that I showed you, where group 1 is going to carry a positive charge, group 2 is going to carry a +2 charge. Halogens are going to carry a -1 charge. Your oxygen family is going to carry a -2 charge, and so on. Transition elements are not going to be able, we can't predict the charges because they can carry different charges. We're not going to be able to predict transition metals. Here is something for you to practice. Classify each substance as an atomic element, molecular element, molecular compound, or ionic compound. Oh, I don't have the answer. Okay. Krypton will be considered an atomic element. Cobalt chloride, cobalt is a metal, so it's going to be an ionic compound. Nitrogen is N2. It's going to be considered a molecular element. SO2, both nonmetals, that's going to be considered a molecular compound. And this is a metal, and this is non-metal. So this is considered an ionic compound. Ionic compound. Another one for you to practice. The first one will be considered, this is your metal and this is your non-metal. So that's an ionic. Non-metal, non-metal, molecular compound. Metal, non-metal, ionic. Lead, it's just Pb. It's going to be considered an atomic element. And this is all non-metals, so it's going to be considered a molecular compound. Question for you to try on by yourself. Write the chemical compound. The compound contains 2 aluminum. So you want to write aluminum, and it is considered that it has 2 for every 3 oxygens. O3. A molecule that contains 1 uranium, uranium is U, and 6 fluorine, so F6. A molecule that contains 4 phosphorus, P4, and 10 oxygens, O10. How many of each? How many magnesium? Well, that 3. How many phosphorus? That 2 applies to the phosphorus and to the oxygen, so it's going to be 2. How many oxygen? 4 times 2, 8. Same thing here. How many aluminum? How many sulfur? How many oxygen? Take a minute to do it by yourself. 4 times 3, 12. Which formula represents the greatest numbers of atoms? So basically you have to go through each. This, how many atoms are here? Well, you have 1 aluminum, and then you have 6 carbons, 9 hydrogens, and 6 oxygens. So you gotta do that for all of them. The answer is gonna be B, but that will check your work. Okay, the next part of this is we're gonna start doing nomenclature. We're going to start naming. So I'm gonna give you, if you don't understand what we just did, I need to rewatch it, because if you don't understand the previous material, naming is gonna become very confusing. So if you don't understand it, rewatch this video before you do the naming video, which is coming up next. Welcome back. We are going to start discussing nomenclature. It means we are going to start naming compounds. We have a systematic way of naming different compounds, which means that we have to follow certain rules based on what elements are coming together. We also have some compounds that have common names. For example, water. Water is a common name. The proper systematic way would be dihydrogen monoxide, but it's simpler just to say water. We are going to learn the systematic way, and and sometimes I will, use the common name too, but you will be tested on the systematic way. In order for us to start naming compounds, it's very important for us to realize what we have, to kind of identify the type of elements that we have. If you have a compound that is molecular versus ionic, so that is the first step when you are naming. Before moving on, you need to identify if, for example, you have, the reason this is going, I don't know why this is going like this. Okay, doing that. CH4, which is a molecular, because they all are non-metal, or things like, give me 1 second. Like lithium chloride. You have a metal and a non-metal. We have two types of, we are going to have two types of naming. We are going to focus on just naming ionic compounds first. What that means is that you have a metal and you have non-metals. We have two types of ionic compounds. We have type 1 and type 2. The type 1 is going to consist of metals that only carry one charge. They only like to form one charge. This is going to be your group 1, your group 2. It's also going to be aluminum. It's going to be silver, and I believe it's going to be zinc. These metals always carry the same charge. Type 2 are going to be your transition metals. They like to carry multiple charge. Based on the type of compound that you have, your rules are going to be different if you have type 1 versus having type 2. Type 1, the metal will always carry the same charge. Type 2, the metal charge is going to vary. Here is the ones in blue at your type 1. Blue is your type 1. And the 10 ones are your type 2, the metals, right? Remember, these are non-metals, so we're talking about the metals. When we are dealing with type 1, the way we are going to name the compound is we're going to be dealing with a binary, meaning two elements. The first one is going to be a metal, and the second one is going to be a non-metal. The first one, you just say the name of the metal. So for example, if you have lithium, you just say lithium. But if you have chlorine at the end, you're going to take the base and change it with I. So chloride, to give you an idea. So here, if you have fluorine, you're going to change the ending into ide, chloride, chlorine, chloride, and so on. And that's how you will name it. So lithium chloride, lithium fluoride, lithium bromide, and so on. Those are going to be your type 1. Notice here we have potassium, so it's the metal. You just say the word potassium, and then you're going to say chloride. Calcium, this is a type 1 because calcium is in group 2. Oxide. Give you a minute for you to start naming those compounds. So this will be magnesium fluoride, potassium bromide, calcium oxide, strontium bromide. We don't use prefixes for ionic compounds, so don't try to say strontium dibromide. No, 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 no. We know the charge because strontium is 2 plus, bromide is -1. When you crisscross, SrBr2. When we are naming our type 2, it's going to be a little bit different. What you're going to do is the metal, you're still going to say the name of the metal. However, in parentheses, you are going to inform us the charge that that metal is carrying when it's with that atom. For example, if in here you have iron, so you will say the word iron. However, in this compound, iron is carrying a charge of 2. The second compound, iron is carrying a charge of 3. So you will have to let us know the charge the iron is carrying. Or for example, copper in this compound is carrying a +1. Second compound is carrying a +2. So you're gonna have to tell us, notice this point, Some may group metals such as lead, selenium, and zinc form more than one type of cation. So you have to be careful. That's why you have the table the periodic table that I gave you. So in general, if you're dealing with a type 2, you're going to put the name of the metal. In parentheses, you're going to put the charge. So the charge could be 1, 2, 3, 4, 5. I don't think you're gonna encounter 6. Those are the possibilities. The non-metal, you're going to take the base of the non-metal and end it with the letters "ide." Okay, so for example, iron 2, iron 3. That's how you are indicating the charge that the metal is carrying. Notice here is, for example, the possibilities. We're not going to be using the old name. We're going to be using the most recent name, which makes things easier. So lead can be lead 2, lead 4, mercury, mercury 1, mercury 2, and so on. Now, obviously, since you're going to have to tell me the charge that it's carrying, that means you're going to have to figure it out how to calculate the charge. In this case, I do not recommend to crisscross. In here, you're gonna be like, oh, iron is 3 plus. Yes, it is, but it's not always gonna be like that. So what you're going to do is, I'm gonna give you an example. In this case, FeCr3, CO3, since there is no charge over here, we're assuming that this is gonna be equal 0 because there was nothing here. So this is gonna be equal 0. So what you're going to do is, we are solving for the charge of iron. We have 1 iron. We're gonna call that charge X plus 3 chlorines. And the charge of chlorine is gonna be -1. Because remember, it's a halogen. Charge of chlorine. This whole thing is going to be equals 0. Then what you're going to do is solve for X. So you're gonna have X minus 3 equals 0. X equals 3. That tells you the charge of iron. Here we have another example, same idea. Set this equals 0 and solve for X. So you're gonna be 1X plus 3 minus 1 equals 0. When you solve for X, it's going to be 3. The proper name of this compound, since chromium is a transition metal, you know that you're gonna have to put the charge. So it's going to be chromium 3 bromide. We have another example here, that one that I calculated. This would be iron 3 chloride. Notice here, this is the, when we're doing Fe2O3, 2 indicating that you have 2 irons, 3 indicating that that's the charge, but let's say we didn't know. So that I gave you Fe2O3. So let's say we didn't know the charge of iron. So what I'm gonna do is set this whole thing equals 0. Iron, we have 2, and we don't know the charge of iron, so we're gonna call it X. Then plus 3 oxygens, and the charge of oxygen is -2. When you solve for X, equals 3. X represents the charge of iron. So what the proper name would be iron 3 oxide. I'll give you a minute for you to try to do this on your own. Oops. Oops. There you go. Take time to do that on your own. The name of the first one, if you got it correctly, would be copper 1 bromide. For the second one, it's asking you for the formula. Be careful with the third one. The answer should be lead, not lead 2, lead 4 oxide. The next one, it's going to be chromium 4 oxide. So another question for you to practice on your own. The answer for this is going to be C. Now, alone ionic compounds, we also have polyatomic compounds. Remember the polyatomic ions. Polyatomic ions are going to be a group of atoms that carry a charge, an overall charge themselves. The reasons why they're considered ionic is because usually polyatomic ions are next to a metal. When we are naming them, we actually need to know the name of the polyatomic ion. For example, you need to know that NO3 negative is nitrate. So the way you will name this compound will be potassium nitrate. In here, because iron is a transition metal, you need to remember that we're going to use a parenthesis. So the answer for this is going to be iron 2 hydroxide, because OH minus is going to be hydroxide. When you have two polyatomics together, for example, NH4 plus is ammonium, NO3 minus is nitrate. So you want to mention both names, ammonium, nitrate. Now, I know for you it may be difficult, but it was going to take a lot of practice, and I've given you a lot of practice on your homework so you can become better at this. This is the table that you need to memorize. The ones I'm gonna cross out, you are not responsible. Everything else you are responsible to memorize. You need to know acetate, carbonate, hydrogen carbonate or bicarbonate, hydroxide, nitrate, nitrate, nitrite, nitrate. You don't need to know dichromate. You need to know phosphate. You don't need to know hydrogen phosphate. You don't need to know dihydrogen phosphate. You need to know ammonium. You don't need to know hypochlorite. You do need to know chloride, chlorate, perchlorate. You need sulfide. You don't need to know that. Sulfate, no, and yes. So you need to memorize this. And I said memorize it because even though there is a way to try to understand how to name him, there are rules. I think the rules are a little bit more complicated than just knowing it itself. For example, it's based on how many oxygens are in that group. For example, the NO family, the one with the most oxygen ends with the word 8. The word with the least oxygens ends up with the word "ite." So nitrate, because it has 3 oxygen, nitrite, because it has 2 oxygen. However, there are other families. For example, the SO family. The one with the 4, because it's the most, ends in the word 8. The one with the least ends with the word "ite." Unfortunately, for you to follow this rule, you're going to have to know how many are in that family. For example, this has 4 in the family. One of them has 1, the other one has 2 oxygens, and 3 oxygens, and 4 oxygen. Therefore, the one with the very least, not only are you adding the word "ite," you also adding a prefix of hypochlorite. Then the following becomes chlorite, then chlorate, then perchlorate. So that's why it becomes a little bit difficult if you don't know how many are in that family. Here's another table that can help you. In my opinion, you can just memorize the ones I gave you. There's a video that will help you memorize them if you want. It's up to you. Why do we care about polyatomic ions? The reason why we care is because we actually use them a lot. They're active ingredients in a lot of the chemicals we use. For example, sodium hypochlorite is an active ingredient in bleach, which we use to clean our clothes. Sodium bicarbonate or sodium hydrogen carbonate, sodium bicarbonate is probably easier. It's baking soda, which we use when we're baking. Or sometimes we put it in the refrigerator to remove odor. We also have calcium carbonate. Calcium is a metal, carbonate is a polyatomic ion. We use that to neutralize when we have acid reflux. We use that to kind of neutralize because it's a base. We also have sodium nitrite, which is an additive that they put in meats, such like sandwich meats and stuff like that, in order to prevent bacteria growth. So it's like a preservative that they add. So this is why it's important for us to know how to at least identify polyatomic ions. Moving on to hydrate. Hydrates are going to be those compounds that are surrounded by water, and they are going to have a salt, and it's gonna be combined with water. So think of wet salt. For example, this is considered magnesium sulfate heptahydrate. The word hepta means 7. The word hydrate means H2O. So that means that that salt is surrounded by 7 waters. This one is cobalt 2 chloride hexahydrate. Why do I have that parenthesis? Because cobalt is a transition metal. In order for us to know how to name hydrates, we need to know the prefixes. Don't worry about hemi, but mono means 1, di means 2, 3 means tri, and so on. So very, very important that you know how to name those compounds. Okay, so that pretty much ends on how to name ionic compounds. When we come back, we'll do molecular compounds. It is time for us to learn how to name molecular compounds. As you recall, a molecular compound, it's going to be when you have atoms that are non-metal. When you are naming it, you're going to be using prefixes. For example, notice here we have nitrogen and oxygen, but it can exist in different combinations, different ratios. What that means is that each of them have a unique name. So you want to keep that in mind. So we're going to be learning prefixes when we are dealing with molecular compounds. For molecular compounds, we are going to usually the element that's going to come first, it's going to be then the element that comes first is the one that you're going to name first. And for example, how do you know which one comes first, nitrogen or oxygen? Well, the one that is closest to the metals it's going to be named first. In this case, nitrogen is closest to the metals. If you look at carbon and oxygen, carbon is closest to the metals. In here, they make it a little bit more complicated. They're saying that if two elements lie on the same group, then write the elements with the greatest rho first. So basically, if I give you an example and I give you oxygen and sulfur, well, you're going to name sulfur first because sulfur is closest to the metals or have a greatest rho number. In general, the metals, if you look at the periodic table, let's see if I have one here. Here's your periodic table. So the metals are going to be this area, right? This area. Oops. It's going to be this area. So as you get closer to this side, your metals are going to increase. And as you go down, the metals are going to increase. So if you look at oxygen and sulfur, sulfur is closest to the bottom, so it's going to be named first. If you look at nitrogen and oxygen, nitrogen is closest to the metal, so it's going to be named first. So that's one way to memorize it. If you look at, I don't know, let's say boron and oxygen, boron will be named first. So let's continue. We are going to, when we are naming this, we're going to be using prefixes. So you put the first prefix for depending on the element that you have, except when the first element only has one, then you don't say mono, you just say the name. Then you name the first element, then you do the prefix of the same element, the second element, and then you take the base and end it in I. So we'll give you some examples, but first, know your prefixes. Mono means one, di means two, tri means three, tetra, four, and so on. So make sure you recall those prefixes because you're gonna be using them a lot. Only for molecular compounds. For example, so what I was telling you that I told you prefix first, then the first element. But when the first element only carries one, we don't say the word mono, we just say carbon. So we're not gonna say mono, we just say carbon dioxide. Di means that you have two oxygens. If you have something like this, then you will say tetra carbon oxide. Okay, so just keep that in mind. So molecular compounds are easy. We are going to be naming acids. Acids fall under molecular compounds because they're all non-metals. Acids are going to start with the element H, hydrogen. Acids are composed of hydrogen and something else, another non-metal. And they are going to be aqueous. So for example, HCl. And if I put aqueous, that means I'm talking about an acid. Now we have two types of acids. We have acids that are only two elements. Those are called binary acids. And we have acids that are more than two elements and they have oxygen. Those are called oxoacids. But before we get into naming them, it's important for you to know some characteristics. No worries, and we will cover an entire chapter of acids. So this is just to kind of introduce you and start recognizing what an acid is. Acids, as I mentioned, they are going to be aqueous. So you're gonna write the word AQ next to the chemical formula, indicating that it's an acid. It's going to start, the chemical formula is going to start with the atom H, hydrogen. Acids have a sour taste. They dissolve many metals such as zinc, iron, magnesium, but they do not dissolve silver, gold, or platinum, which is a good thing. You don't want your chain to be dissolving while you're wearing it. or whatever you have that it's called. Like I mentioned, the formula usually is going to start with an H. I say usually because there's exceptions. You're gonna start realizing that chemistry has a lot of exceptions. This is considered a binary acid. This is considered an oxo acid. Yes, we have two types of acid. When we only have two elements, one of them has to be hydrogen. Those are considered binary acids. And we have one set of rules for that. Once we start having more than one atom, and it includes oxygen, it's considered oxo acids. Now, how do we name this? If we have binary acids, we have one set of rules. Remember, those are the ones that only has two elements. Oxo acids have oxygen in it, and most likely that oxygen is going to be part of the polyatomic ion. So you want to make sure you are careful and identify them. Let's start by naming our binary acids, meaning those acids that only have two atoms. One of them is being hydrogen. You're going to start with the word hydro. Then you're going to take the base of the non-metal and end it in ic. And then you're gonna say the word acid. So HCl will be hydrochloric acid. HBr will be hydrobromic acid. I apologize for my puppy. He has his own mind. Brat, I'm telling you. Anyways, moving on to oxo acids. Oxo acids are going to be those acids that also start with an H and also have aqueous, but they contain oxygen, and that oxygen is going to be a part of the polyatomic ion. Now, it is highly important to know what polyatomic you have. For example, here that oxygen is part of nitrate. Important because we care about the ending. So learning your polyatomic ions is very important. This oxygen is part of a polyatomic ion, sulfite. Notice that this is sulfate. Yes, that means they're gonna be named different. So if that oxygen is part of a polyatomic ion that ends in 8, we are going to change it to ic. For example, HNO3, this is nitrate, right? So we're gonna call it nitric acid. Nitric acid. Okay? But for example, if you have something that ends in I, so you have to go back to your polyatomic ions and look what ends in ite. So for example, if I have HNO2, what is NO2? Nitrite. So the name of the acid will be nitrous acid. Notice that we do not use the word hydro in oxo acids. We do not use the word hydro in oxo acids. Here is for you to practice. First, ask yourself a question. Is it a binary or is it an oxo acid? So this is a binary oxo acid, oxo acid. So if it's binary, you're gonna start with the word hydro. And then you just take the base, so it'll be hydrosulfuric acid. Here, identify the polyatomic ion. What is this? This should be chlorate. And what is this? Acetate. So it will be chloric acid and acetic acid. Here are your answers. So as a summary, if the ending is in ic, you're going to change your polyatomic. If your ending of the polyatomic is in 8, your acid is gonna end in ic. if your acid, polyatomic ion ends in ite, you're gonna change it to OUS. That should be, yeah, ite, not, yeah. Okay. So in summary, this is the part of, this is the chart that will help you with the acids. Notice here, this is nitrite, nitrose, nitrate, nitric, sulfite, sulfurous, sulfate, sulfuric, and so on. So important table to go over. And this is the summary of all the naming that we have done. This concludes the naming. The rest of the chapter will just be math, and I'm gonna cover all in one video. So get ready. Maybe we'll cover it into because it's a lot, but all the naming is done. Make sure if you wanna stop here and do some of your homework for naming and come back, that would be a good idea. Okay, let's continue our discussion. And now we are going to teach you how to calculate the formula mass, which I kind of already mentioned it. When I say formula mass or formula weight, you want to remember that the unit is going to be AMU. So sometimes they call it molecular mass or molecular weight. Basically, what we're doing is adding the mass of all the different atoms. For example, in water, we are going to have 2 atoms of water, and we are going to multiply it times the atomic mass, 1.01. And then we're going to add it to how many oxygens. There's only 1 oxygen, and we're going to multiply it times the atomic mass, which is 16. So 2 times 1.01 plus 1 times 16, the total should be 18.02 AMU. And that's how we calculate the formula mass. For example, here, this is chloroform. And if we wanted to calculate the formula mass, we will know that chloroform has 1 carbon, and the atomic mass of carbon is 12. There is 1 hydrogen. The atomic mass of hydrogen is 1. There's 3 chlorines. The atomic mass of chlorine is going to be 35. When you add all of those numbers, the answer should be 119.37 AMU. This is table sugar. If we were to calculate the atomic mass, which pretty much will do 12 times, I think the mass is 1201 plus 22 times 1.01, 008 plus 11 times 16. And when you do all of that, that should give you your final answer. Here's one for you guys. Notice how we have aluminum. Remember, aluminum is a metal that's whose charge doesn't change. And aluminum, and what is this? Sulfate. So the atomic mass, when you do it, will be 342.14 AMU. What about this? Calculate the mass of an anti-caking agent, and it's called calcium phosphate. So notice that the only way you can know how to do this if you know the formula. What is calcium? Calcium is Ca. What is the charge of calcium? Plus. What is phosphate? Phosphate is PO4 2 minus. So what we're gonna do is gonna become, sorry, it's phosphate 3 minus. So what we're gonna do is crisscross. So Ca, phosphate is a polyatomic, so we're gonna open parentheses. Phosphate, sorry, 3, 4, 2. phosphate, parentheses, PO4, the 2 comes from calcium. Now the atomic mass, once you calculate it, will be 3.1018 AMU. But the only way you get this number is if you know the correct formula. How will you answer this question? Well, the reason why this is incorrect is because calcium, it's in group 2, which means its charge never changes. The name of the compound NCO3 is named nitrogen trichloride. What is the name of this? First, you want to ask yourself, is it ionic or molecular? It's ionic. Is it group 1 or group 2? Group 1. Why? Because of the aluminum. So the name of this would be aluminum chloride. We don't use trichloride because it's an ionic compound. What is the answer for this? The greatest formula mass. The answer will be, okay. On the same idea, let's teach you how to calculate the molar mass. The molar mass, you calculate it the same way. What's going to change, it's going to be the unit. The unit is going to be grams per mole. Notice here that in here where it says the formula mass, we calculate it the same way, but the unit is AMU. On the other hand, if we are talking about the molar mass, the answer will be grams per mole. So we are going to calculate the same way. This is kind of just going over what we did, and we're gonna use it to do conversions. So for example, where we are using conversions to go from grams to moles or moles to grams, we're gonna use the molar mass in order to convert. If you're using molecules to moles, then you're gonna be using Avogadro's number, which we went over the last chapter. Now, we're gonna start being able to come out with our own chemical formulas. And what we're gonna be doing is sometimes they're gonna be giving us percentage, and we're gonna convert that into a chemical formula. And basically we're gonna know those subscripts that we were seeing, and we are going to do some examples. But before we get to that, we're gonna know, for example, if I give you water, H2O, and I ask you what is the percent of oxygen. So you should be able to tell me what is the percent of oxygen in this compound. Or what if I give you carbon tetrachloride? What is the percent of carbon in this compound? So you're gonna have this equation in order to determine the percent of a specific element in that compound. The way we're gonna do it is pretty much part over whole. You take the mass of the elements and you multiply it by how many atoms you have of the element, and then you're gonna divide it by the mass of the total compound. Pretty much mass of part divided by mass of whole. It's not complicated, I promise you. Let's give you an example. So let's say I give you, it says a 0.358 grams of chromium reacted with oxygen to form a metal oxide. What is the percent of chromium in this in this compound? So the part is gonna be 0.358, and the whole is gonna be 0.523. So that times 100, the answer is 68.5% in that compound is chromium, and the rest will be oxygen. Now, when you are giving that, basically we wanna assume we're gonna be able to use mass percent composition as a conversion factor. And the reason for that is we're gonna assume that we are giving 100 grams. So for example, for sodium, we're gonna use 39 grams, 39%, which means 39 grams over 100 grams of sodium chloride. So meaning this, sodium chloride, and we're gonna say that in this case is 39% is sodium. What that means is there's 39 grams in 100 grams of sodium chloride. How did I come out with that number? Well, that's, hold on a second, we need a periodic table. We are going to need, well, you don't need it, I'm gonna need it so I can see the numbers. So if we look at the mass of sodium, it's gonna be 22.99. Then the mass of the whole will be 22.99 plus, and what is chlorine? 35. So this will be 22.99 divided by 58.44 times 100. That will give you 39%. That's where the 39 comes from. So we're going to use that as a conversion factor. So in sodium chloride, 39% of it is sodium, or we can say there's 39 grams if you have of sodium if you have 100 grams of sodium chloride. So that's what we're going to be using it now. Let's do some math to see what I mean. For example, the FDA recommends an intake or a consumption of 2.4 sodium chloride of sodium per day. However, we can't just take the sodium, right? We use, the way we intake the sodium is by using sodium chloride. So the amount that we allow is 2.4 grams of sodium. We're gonna use this, the percentage, as a conversion factor, which means 39 grams of sodium, assuming we have 100 grams of sodium chloride. This tells us that we are allowed to consume 6.2 grams of sodium chloride daily and still be within the limits that the FDA recommends. Here we have another problem. If I ask you what is the percent of chlorine in this compound? Well, how many chlorines do you have? 2. And then what is the mass of chlorine? It's 35 point something, 35.45, I believe. Yeah. And then what you're going to be, so it will be 4 times 35.45. And then this 203.8 represents the entire mass of that compound times 100. In this compound, what it's saying is it has 65.58% of it is chlorine. So I'm gonna give you time for you to calculate that problem. And here's the answer. Here's another problem. I don't have the answer, but the first thing you wanna do is calculate the molar mass of this. And then you're gonna do 6 times 12, whatever that gives you, right? That's how you're gonna calculate it. And then you're gonna do 12 times 1.008, and then 6 times 16, And that number will give you the entire molar mass. And to calculate the percent of carbon, so this is the total, you're going to do 6 times 12 divided by the total times 100. To calculate oxygen, you're gonna do, oxygen is 6. 6 times 16 divided by total times 100. If you want to calculate the percent of hydrogen, you're going to do 12 times 1.008 divided by the total times 100. And we can do it together if you guys did not get this. Here's another problem. Here's the answer to it. Okay, now let's talk about the empirical formula. I don't have the answer to this, but we can do it later if you like. We already went over what the empirical formula is. The empirical formula is going to be the simplest whole number ratio of atoms. Now, we already know how to go from the molecular formula to the empirical formula. We find the greatest common factor and we divide everything by that to give you the lowest ratio. So that's good. Now we need to know how to go backwards. If I give you the empirical formula or if I give you percentages, how can you give me the molecular formula? So, couple of things. When you are giving, you're going to be even giving percentages or you're going to be giving that empirical formula or just grams. If you are giving percentages, you're going to assume that you're giving grams. So I know this sounds a little bit confusing, but we're going to go through it. So here are the rules. First, you are going to be, if you're giving percentage converted to grams, assumes that you have 100 grams. It might be helpful if I skip to the problem itself. For example, here. In this case, they didn't give you grams. I mean, they didn't give you percentage. They already automatically give you grams. So step 1 on those rules, you can skip it. The second step is convert the grams that they were given to moles. So they give you 3 grams of hydrogen. So you want to convert it to moles using the molar mass. And you want to do the same for oxygen. So that's rule number 2. So you want to go above and see the rule. The next one is rule number 3, which means write a pseudo formula, meaning write a fake formula. That fake formula is pretty much going to be H3O1.5. That's the pseudo formula. Step number 4, it says to divide by you're gonna divide by the smallest number of moles. In this case is 1.5. So when you divide that, you're gonna have H2O, right? Because 1.5 divided by 1.5 is 1. In this case, since you have no decimals, just full numbers, this becomes the empirical formula. If you finish and you ended up with decimals, you're gonna have to figure it out what number to multiply it by to get rid of that decimal. Don't worry, this chart will be provided for you. So for example, if you ended up with H2.5, you're gonna see, hey, here's 0.5. I'm gonna multiply this whole thing by 2. So you will multiply this by 2. So 2.5 times 2 should be H5O2. And this will be the empirical formula. So let's give it a try. Here they're telling us that you have a sample. So you have a sample, 3.24 sample titanium that reacts with oxygen to form that much metal oxide. So first, you don't have, what they're saying is you have titanium plus oxygen and you ended up with metal oxide. They're telling you that this is 3.24 and this is 3.24. Oops, 5.40. However, you don't know how much oxygen. Remember, matter cannot create it nor be destroyed. So what does that mean? In order to find oxygen, you're gonna do 5.40 minus 3.24. That gives you how much oxygen you have, which is showing here. Now that you have that, you're gonna move to step number 2. You wanna convert those to moles. So here's you're converting your titanium grams to moles, oxygen grams to moles. The next step is to write a pseudo formula. A pseudo formula, this is the pseudo formula. The next step is to divide by the smallest number of moles, which in this case is gonna be 0.0677. Notice that when you do that, you end up with that empirical formula. And that's your empirical formula because you have no decimals. So that will be that last step. Let's go over one together to see what I mean. So here they're giving you percentages, okay? And the solution is coming up. But since they're giving you percentage, you're gonna assume that you have 100 grams. So automatically assume that you have 60 grams of carbon, 4.5 grams of hydrogen, and 35.5 grams of oxygen, okay? Now, step number 2 is to convert it to moles. So you're gonna do 60.0 grams of carbons, and you're gonna convert it to mole. You want grams at the bottom, and the mass is 12 grams per 1 mole. That should give you 5.0 moles. Then you do the same for hydrogen. 4.5 grams of hydrogens times 1 gram of hydrogens and 1 mole of hydrogen. That gives you 4.5 moles. The next one is oxygen, which you have 35.5 grams of oxygen converted to moles. The answer will be 2.22. The next step, so this is step number 2. The next step is to write a pseudo formula. So you're gonna write carbon 5, hydrogen 4.5, and oxygen 2.2. The next one is to divide by the smallest number. In this case, it's gonna be 2.2, 2.22, right? Yes. So you're gonna be 5 divided by 2.22, H 4.5 divided by 2.22, oxygen 2.22 divided by 2.22. Then you're gonna realize that your answer is going to be carbon 2.25, hydrogen 2, and oxygen 1. Now this is not the empirical formula because you have a decimal. You're gonna look at that table. You're gonna realize that at that table, if you end up with a 0.25, you should multiply everything by 4. So this whole thing gets multiplied by 4. So it's gonna be carbon times 2.25 will be 9. Hydrogen, 2 times 4 will be 8, and oxygen will be 4. This is the empirical formula. And you're done. So here are the steps. So you can try to do it by yourself if I was going too fast. And that is your answer. Now, so this table will be provided for you. Now, this is the empirical formula, but we need to get to the molecular formula. So how are we gonna get to the molecular formula? The way we're gonna get to the molecular formula is, no, ignore that slide, is by taking that empirical formula, figuring out the molar mass, and I will be giving you the real molar mass. And from here, when you divide the mass that I give you, divided by the molar mass of your empirical formula, you're gonna have a number. You're gonna take that number and multiply your empirical formula by that number. And that should work out. So for example, in here, let's say I tell you that this is the empirical formula, and I tell you that the molar mass is 180.2. How will you calculate that molecular formula? Well, first, N equals, you're going to take the number that I give you, 180.2 grams over moles. And then find out the mass of that, which is gonna be, of that empirical formula, which is gonna be 30.03 grams over mole. So that should be 30.03 grams over mole. Units cancel. Your answer is gonna be a number 6. So what are you gonna do? You take this CH2O and you multiply it by 6. So you're gonna end up with carbon 6, hydrogen 12, and oxygen 6. And that will be your molecular formula. And you're gonna have something like this on the exam. So this is the empirical and this is the molecular formula. Here is the answer. And here are the steps. Use the molar mass, which is given, and the empirical formula mass, which is the one you're gonna calculate. You're calculating based on your empirical formula. You're looking for N. And what you're going to do once you find N, you're gonna multiply the subscripts in the empirical formula by N to arrive to the molecular formula. Here's an easy example. Notice in here, I'm giving you the molar mass. Okay, so that number is going to be at the top, the number that I give you. Remember, your goal is to calculate N. And they're telling you that the empirical formula is CH. So calculate the molar mass of that. So it's gonna be 12 plus 1 is gonna be 13 grams per mole. So you're gonna divide it by 13 grams per mole, and it's gonna be 6. So you're gonna take CH times 6, C6H6 is the molecular formula. Here's the answer. Try this on your own, and we can do it as a group later if you don't understand it. But I really, really encourage you to try it on your own. So notice that because you're gonna have something exactly, almost exactly on the exam. Here you go. So the empirical formula is this. And here is the molecular formula. And this is the end. We are not going to name organic compounds. I'm gonna leave that until the end later on for organic chemistry. I think that's it for now. Later on, we're gonna discuss functional groups and stuff like that. But for right now, this is the end of the chapter. and we'll continue later on.